Okay, this is mechanics term 2 week 5, 4.4 to 4.6. There's a bit of new stuff. It has to do with the change. I'm not going to start with my notes. I'm going to upload them to my drive because I was absent for a week, so I have notes missing. Anyway, it has to do with change in potential energy. Potential energy is denoted by U. There are two types. We have U elastic and we have U gravitational. Okay, gravitational potential energy GPE is just equal to mgh, right? U elastic is equal to elastic potential energy, and it's actually half kx squared for the spring, in case anybody is confused. Okay, you know the spring elastic potential energy is half the spring constant times elongation squared. Anyway, today our lesson is about the first thing you need to know is that mechanical energy is conserved. Mechanical energy 1 is equal to mechanical energy 2 if the only force on it is a conservative force. In other words, conservative force is a force that doesn't waste energy, like weight. Yeah, that's a conservative force. But stuff like friction and air resistance, those are not conservative because they take away some energy and like release it outside. So if you have friction and air resistance, mechanical energy 1 equals mechanical energy 2 will not be applicable. The second thing is what's it called? Is this. So we know that U is potential energy, and it's equal to integral of the force, right? So if you derive both sides, you actually find out that the force is actually equal to derivative of U over dx. You're not responsible on this. But anyway, force, if you want to find the force, it's actually just the derivative of U by dx. That's pretty much it, yani. Okay, so anytime you have a change in potential energy, there is a force. That's all you have to know. So I'm going to show you a graph so you can better understand it. So it's equal to negative du over dx. Okay, it's always opposite. So I'm going to draw a graph for you. I'm going to draw it. I'm going to start like this, and it goes constant over here. Okay, so I'm going to label this as U in joules, and over x, let's say meters. X in meters, right? Okay, so there are two things you need to know over here. U is changing, it's going down, right? Remember, force is equal to negative. So if U is decreasing, then force in this case is positive, right? So it's positive. Even though U is decreasing, force is always the opposite. Now U is going up, right? That means the force is decreasing over here, okay? Over here, you have a constant, no change. What does that mean? Force is equal to 0 because there's no d, there's no change. Okay, so that's very easy. There are three things you need to know. There are these 3 points: one here, and one here. Okay, obviously the derivative equals 0 at this point because it's not changing, and also at this point and this point. Why? Because from math, you guys know that these are turning points. At the turning point, the derivative equals 0, right? Anytime the derivative equals 0, when du over dx is equal to 0, so anytime you see a turning point or a constant straight line equals 0, then the force is equal to 0, and we say it's in equilibrium. And there are three types of equilibrium, okay? Stable, unstable, and neutral. If you want to pause the video and guess which one of these are which, so which one is stable from these 3 points, this, and this, and try and guess which one is which, you can be my guest. But I'm going to give it to you right now. This is the stable equilibrium is over here, because if you imagine a ball, if you put it over here and you pushed it to the left, it's just going to roll back down. Okay, this one over here is unstable. Again, imagine the same example. If you had the ball over here and you pushed it a bit to the left, it's going to fall all the way down. Okay, so it's not going to go back to its original position, so it's unstable. And then over here, it's neutral. If you had the ball over here, you pushed it to the right, it's going to stop there. You know, it's a straight line. Okay, although it may not be straight in my drawing, not perfectly straight, but the whole point is that it's neutral, it's straight. So this is neutral equilibrium, this is stable equilibrium. So this is very, very simple. We're going to start now. Here, kinetic and potential energy are recorded over a period of t seconds. So we have energy. Both quantities appear to increase linearly with time. So we're seeing that there is a change in energy. What does that mean? That means there's a force. So forces are balanced. Does that mean the force, when forces are balanced, it means net force is equal to zero? Obviously, that's wrong. There's dissipation of heat. Yani, are we losing energy? No. Well, how? A non-zero net force exerted. Yes, we have a. Remember, we said there is a force. Since there's changing, force does not equal zero. So that means there is a force. Okay. A work is done. Obviously, a work is done. You're putting a force through a distance. The particle is in stable equilibrium. It's not necessarily. You don't know. You never know. Okay. The power developed by the net force acting on the particle is constant. You're going to say, how is it constant? Here they said the energies are increasing linearly. Okay. Power is what? I forgot to mention this. Okay. Power is work divided by time, and the other formula is power is equal to force times velocity. Okay, that's later. Okay, but anyway, work divided by time, so it's the change in energy per second, right? طب نحن we're saying that the change in energy is linear. You know what linear means? It means this, and it's increasing at a constant rate. It's not a curve, no. Okay. Also, it was in the book. The book actually told us you can work with energy time as if it was an xt graph. So actually, why we say this is, remember when the xt graph was straight, if you remember, velocity is the derivative of displacement. The same way that this is E, not F. I don't know. It looks like an F. The same way that power is the derivative. It's the derivative of work with respect to time. It's the change in work with respect to time. So remember, if the displacement was constant, then the velocity graph would look like this. Right? Same thing with energy. If it was straight, that means it would look like this. The power graph. The same thing goes if it was curved, and so on and so forth, so I'm not gonna waste my time. I think you get the idea. Okay? Power is equal to work divided by time. Since the work is increasing at a constant rate, then obviously the derivative will be a straight line. I think you all know the derivative of a straight line. What's the derivative of 2x? It's 2. It's a constant value. Okay? Question 2. A ball is released from rest 7 meters above the ground, so they gave you height. G, it gave you G. They said drag force is negligible, so what's the ball speed as it's about to hit the ground? Okay, when you see that they're saying drag force is negligible, they're trying to tell you, no, okay, there wasn't any energy lost, because drag force is like air resistance. That means there wasn't any energy lost. Anytime you see a question like this, height, whatever you want speed, think conservation of mechanical energy. Okay, ME1 is equal to ME2. Some people, they write this. They write GPE, UG is equal to the kinetic energy final. You can do this, it's normal. But why do I write this for you? Because if you don't write this, you don't get a mark in Sabis. Okay, from what I know. Okay, so mechanical energy 1 is equal to mechanical energy 2. Or you can just simply write, because what is mechanical energy? I'm sure you guys all know mechanical energy is equal to kinetic energy plus potential energy, right? If it's a spring, it's not only the gravitational potential energy, it's also elastic. But we don't care about elastic right now. Anyway, what I'm trying to say is mechanical energy is the sum of kinetic and U. I'm going to show you why people write what I showed you earlier. Okay, so kinetic energy 1 plus U1 is equal to kinetic energy 2 plus U2. So you're dropping a ball from above the ground. When the ball is up here, okay, kinetic energy, is half mv squared. U is mgh, right? Gravitational equals k2 half mv2 squared, right? Plus u2 mgh2. So at the start, for looking at kinetic energy 1, the ball, it was at rest, right? It's released from rest. It was released, so v1 is equal to 0. So do you think there's going to be half mv squared? No, it's going to be 0, right? Because since v is 0. mgh, the mass of it is, you don't know the mass, so we're going to keep it as mgh. Okay, I'll show you how you get rid of it later. Equals half mv2 squared. We know now in the second phase when it's falling, Obviously, it has the velocity, so it's not going to be cancelled. Plus mgh2. Obviously, this is going to be cancelled to 0. Why? Because when it falls, خلاص, its height is 0. So it's going to be cancelled. So هلا you're left with mgh is equal to half mv squared, mv2 squared. Okay, you can cancel m with m. Okay, and you're left with gh equals half v2 squared. Multiply by half, divide by half on both sides. Or in other words, you just multiply by 2 on both sides to get rid of the half. So you're going to get 2gh is equal to v2 squared. So v is equal to root 2gh. So root 2 times 9.8 times 7. You should get 11.7. Let's see. 2 times 9.8 times 11.2. 2 times 9.8 times 7. What am I doing? You get you get 137.2 square root. You get, let me take this down, 11.7. Very easy. Many people just use the formula. So by the way, you see here now, I was left with u is equal to k2. Okay, they use this directly, which is there's nothing wrong with it, but I like using this so and you can kind of understand. In the exam, please don't waste your time. Write k1 plus u1 equals k2 plus u2. بسرعة check. At the start, it was at rest, so k1, you get removed. Okay, these are things speed up your solving speed. A motor consumes 600 kilojoule of energy, does 150 kilojoules of work. Obviously, what's the efficiency going to be? Efficiency is going to be work out over work in times 100. So it's going to be 150 over 600 times 100, which is 25%. Question 4. A water pump lifts 4 kilograms of water up 1.5 meters every 5 seconds. What is the power of the pump? Obviously, power is equal to work over time. What's the work? Work, we know, is force times distance. But here, ما عندك force, you're lifting water up. Let's try and recall the cases of work. Remember, work goes up. Okay? What is the force of water? Water, how do I say this? Let's imagine this is any object, okay? Its weight is pulling it down, right? You want to push it up, so the work you're going to do is going to be like this. When you push it up, the amount of force you're putting in should be equal to the weight, right? So the force is actually equal to the weight. So my force is actually mg. And you're lifting it, remember work is equal to force times distance. The force, it's mg. The distance is going to be the height, 1.5. So mg times h. In other words, remember we said that work is actually equal to negative ug. This was a formula we had. What is negative ug? Ug stands for gravitational potential energy, GPE, which is just equal to work is equal to negative mgh. Okay, I know I'm talking too much, but I'm trying to give you as many formulas as I can. You can find one you're comfortable with and do whatever you want. Okay, so work over time. Work is a form of energy. You're lifting something up. Anytime you lift something up, think gravitational potential energy. Always. You're lifting something up, always do mgh. Okay, gravitational potential energy. Over the time, now solve. M is 4, G is 9.8, T is 5, I'll shoot T, as the H is 1.5 over 5. Let's see. It's fast. 4 times 9.8 times 1.5 divided by 5. You get, obviously, 11.8, 11.76. Question 6. Okay. The graph below shows the variation of potential energy of a particle at different locations along the x-axis. The straight line is tangent to ux graph at x equals 10 meters. One thing I forgot to mention was the mechanical energy graph. So, same thing as up, when you have a U in joules, obviously, and you have, let's say, here it was meters, right? X, yeah. And then x meters. And you draw your nice graph over here, whatever. Okay? Let's say this is U, goes maybe from 80, تنزل negative, I don't know, 40. Let's say I told you that the mechanical energy is equal to 40 joules. Here is what you do, and you pay attention very carefully. You go to 40 on your graph, which is over here, and you draw a line like this. say وليد شو استفدنا. Okay, here is U, right? This is U. Okay, yeah, so I froze for a sec. I don't know what I forgot. But basically, let's say they came and told you the mechanical energy is 40 joules. You know that this graph is potential energy. And you know mechanical energy. Okay. So, this 40 joules, sorry, yeah, this graph is potential energy. You know mechanical energy is potential energy plus kinetic energy. Okay, so think about it like this. 40 joules, it goes down. Here, potential energy is less than 40. So that means to make up for the other part, it needs to reach 40. The total has to be 40, right? The mechanical energy. To make up for it, there will be a kinetic energy. So for example, when the object is here, it has, let's say, 20 joules potential. How much kinetic will have? Since it has 20 potential, you do 40 minus 20, and that means 20 will be for the kinetic at this point. However, here, مثلا, at like negative 30 or the whatever, you do 40 minus 30, and it has to be 70, whatever, and so on and so forth. Okay? So someone's gonna come and ask me, okay, what if over here? It's very simple to say that the particle will not exist over here because it can't have more energy than the mechanical energy. Simple as that. Okay, the particle will simply oscillate between these 2 points. Oscillate as in it comes left and right. Okay, so let's continue. We have our first graph here. This shows the graph of potential energy with respect to this displacement. The straight line is tangent. They gave us a straight line. So they actually gave us the straight line. They gave us the tangent, which we'll use in a sec. The initial mechanical energy is 60 joules. So what's the mechanical energy? 60 joules. So we can put a nice line like this. Okay. The particle is in stable equilibrium where? Obviously, it's in stable equilibrium over here when it turns, right? So over here at 8 meters. Very easy. The kinetic energy of the particle when it's at position x equals 4. So over here at x equals 4, it's at how much? 45. Because it's 1, 2, 3, 4 spaces, and it's 20 in between. 25 by 4 is 5. So this is 45 over here. Okay, so it has 45 U, right? So potential energy is 45. We know that the mechanical energy is how much? 60. So how do you find the kinetic? 60 minus 45, and you get 15. Simple as. Then they say the force F on the particle. When you have potential energy and you have, let's say, when you have potential energy in a graph, we know that the force is equal to the derivative of potential energy with respect to time. We said it a shoe time as with respect to x. Okay? And it applies for other planes as well. It was in the book. I don't know if there's any question about it in this quiz. I didn't really check. But force is actually equal to negative derivative of u with respect to x. Okay, this sign is another way for d. It's just the way they wrote it. If it's in a two-dimensional plane, comma, negative du with respect to y. If it's in a three-dimensional plane, which I solved an activity about, it's also negative derivative of u with respect to z, because you know it's x, y, z, right? This is just things in case it comes and they gave you a vector that's like 7x squared I plus 3 y to the power of 5j plus 12z to the power of 4 k, because you know it's I, j, k, x, y, z. If this comes, they ask you to find the force. Simply derive one by one. Okay, you can put the negative outside and do it, or do negative, whatever you want. It's fine. Okay, this is just a quick formula I have to give you in case it comes. So the force is always just take the derivative. طيب نحن what we need to derive? We need to derive at x equals 10 meters. We need to take the derivative at x equals 10 meters. In other words, we're finding the slope. Okay, when we want to find the slope of the derivative, value of the derivative, isn't that finding the slope of the tangent? Yes, that's why they came and drew for you the tangent over here. So to find the slope of the tangent, I can't really see proper points. I can see over here 8, 0, and I can see, I think that's 11, 20, right? So we can find the slope from doing this. y2 minus y1 equals x2 minus, over x2 minus x1. So 20 over 11 minus 8. So 20 over 3. And remember, it has to be negative, right? Negative outside. So negative 20 over 3, which is negative 6.7. Okay, simple as. Question 6. Again, another graph. The potential energies, so it gave us a graph over here. The potential energies corresponding to the stable positions of the particles are what? We have stable position over here, stable position over here, and a stable position over here. Realize how they said stable. They didn't say equilibrium. If they said equilibrium, you'd have 1, 2, 3, 4. But here, we only took these two. Why? Because they said stable. Stable, remember, it's only when it's at a minimum. This is stable, okay? Think about it as a ball. Remember, if you push a ball here, it's gonna fall off. Okay, but if you push a ball, if you push a ball over here, it's just gonna slide back down. Type anyway, chop chop. So what is the energy over here? It's 3, and over here it's 9. Very easy. Type. A particle with a total mechanical energy of 20 is placed at x equals 3.8 meter. Okay, so 20 joules is the total mechanical energy, so over here. And it's placed at x is equal to 3.8 meters. So over here. So over here, we have a change in potential energy. So anytime, remember, anytime you have a change in potential energy, you will always have a force. The force is equal to what? The force is equal to negative derivative of u with respect to x, right? طيب, negative, right? Here my change is positive, so negative of a positive value, so أكيد the force is gonna be negative. Please correct me in the comments if I'm wrong. But this is why I think it's directed towards origin. If a force is positive, it's gonna pull you away, right? If a force is negative, it's gonna take you back to the origin. That's the only reason I think it's towards origin. Please correct me if I'm wrong in the comments. Part C, a particle has a total mechanical energy of 10 joules. In which of the following positions can this particle be found out? So go to your graph, go to 10 joules, and let's check. 0 meters, no, because 0 meters it's above. Remember, we're not allowed to be above it. 2 meters over here, it's below عادي. 4 meters, it's over here. أكيد لا. 6 meters, it's كمان above. فلا. و 9 meters, عندك هون it's below. That's correct. Okay, so 2 meters and 9 meters only. Question 7. A block of mass 500 grams is attached to a spring of natural length 15 centimeters and constant 100 Newton meter. The spring stretches by 5 centimeters. While elongation x is equal to 0.05 meter. I like keeping it in meter. The spring is hung from a point 50 centimeter above the ground and the block is released from rest. Ug equals 10 and choose the zero level of potential energy on the ground. Further saying, use this as a reference point. The elastic potential energy. Fast. We can do step by step. But we have a spring over here, its natural length is 15 centimeters. Okay, when you attach this block now, the spring stretches by 5 centimeters. فهلا it's gonna be كلها 20 centimeters, right? You're gonna need this y for later. Anyway, if this is 20 centimeters, this is gonna be كلها 30 centimeters. Anyway, the elastic potential energy. U elastic has its formula. Elastic potential energy is half kx square. ما في أحلى من هيك. half k is the spring constant, so 100, x squared, so 0.05 squared. X is not the length of the spring, it's the elongation. It elongated 5 centimeters. Okay, فبتحط هلا على الكالكوليتر. Half times 150, 50 times 0.05 square is 0.125. So they said to 2 decimal places, أكيد it's gonna be 0.13, right? Correct. First one correct. Type. The gravitational potential energy of the block. So, the gravitational potential energy of the block. So, the block is over here at the height of what? Remember, this is why I drew for you the 20 centimeter and 30 centimeter. Gravitational potential energy UG is equal to mgh. Its mass is 0.5 kilograms. Its g is obviously 10. And the height. The height is what you needed to find by yourself. Most people don't draw this 20, 30 thing, so I'm just going to redo what I did. Okay, you need to know the height of where this block is. They give you هيدي كلها 50, so you need to know how much is this, right? They said that the spring is 15 centimeters naturally, and once you place the block on it, it elongated by 5 centimeters. So in total, عندك هلا 20 centimeters. So this is all 20 centimeters, meaning that what is left is only 50 minus 20 centimeters, which is 30 centimeters. So the height in meters, it has to be in meters always, 0.3. Okay, so you're gonna get should be 1.5. Yes, it's 1.5. Do it on your calculator if you don't believe me. The spring is cut by scissors and the block is allowed to fall to the ground. The speed with which the block hits the ground is what? Always, whenever you have released and falling to the ground, use mechanical energy 1 is equal to mechanical energy 2. Mechanical energy 1 is U1 plus K1 is equal to U2 plus K2. In the exam شو بتعمل؟ بسرعة you write half mv squared 1 plus mgh1 is equal to half mv squared 2 plus mgh2. Okay, don't waste your time, take this. Okay, طيب, let's see. At the start, obviously the velocity is 0, so you cancel it. Okay, because you're at the top, right? When it falls down, the height is going to be 0, so h2 is going to be cancelled and put 0 above it. So you're going to get this, so let's do it. mgh1 is actually what we calculated earlier, 1.5, is equal to half the mass, 0.5, times v squared. But you can easily solve this. Multiply by 2 on both sides to get rid of the half, it's going to be 3. And then you're going to get, yeah, okay, half times 0. Whatever, solve half times 0.5, so 0.5 times 0.5, because half is 0.5. 0.5 times 0.5 is this, 1 over 4. Okay, then divide, okay, yeah. I want to solve it fast, but some people, they get confused, they don't know how to solve math, and they get lost, they're like, oh, he went too fast. Okay, so now you divide by 1.5 on both sides. As you divide by 0.25 on both sides, you get 6, and then v squared equals 6, so v is equal to plus minus 6 meters, root 6 meters per second, right? Square both sides, or square root both sides. You should get 2. To one decimal place, it should be 2.4. 2.4. كيف اجت لون هي؟ Okay, I got why I got it wrong. I was stupid. I even said this in my own video and I forgot it. Mechanical energy is equal to the sum of all energies, potential and kinetic. But remember, potential can be gravitational and elastic. That's why we found both types at the start. Okay, so when in the case you have elastic potential energy, akid you have to add it. Okay, you have to add it. Okay, so mechanical energy actually it's equal to UG plus kinetic energy. Plus, in the case of a spring, you add U elastic. In this case, we have a spring, and I forgot to add U elastic. And we found how much was U elastic, how much was elastic energy? 0.13. So you just add a 0.13 over here. Okay, and let's solve again. So 1.5 plus 0.13. Okay, and then you divide by 0.25 on both sides. And then square root. And you get 2.55. It's positive because they said speed, huh? So 2.55. To one decimal place, it should be 2.6 meters per second. Yes, perfect. Okay, so this should be, ignore this. It should be v squared is equal to, v is equal to, whatever. You get v is equal to 2.6. Question 8. A mass 500 grams, a toy car mass 500 grams rests on the ground next to a 180 centimeter bookcase with 6 equally spaced shelves. 180 وكلهم 6 shelves, up until 6 shelves. So okay, each one should be 30. The net mechanical energy of the toy car relative to the second shelf. So the car relative to the second shelf is negative 3 joules, which confirms that the car is below it, right? UG equals 10 meters per second square. The toy car will have a 0 net mechanical energy at a height of where? Okay, when will it have 0 mechanical energy? Remember, mechanical energy is equal to gravitational potential energy plus kinetic plus elastic if you have a spring, but see, we don't have a spring. What's important here? They're saying it's resting. Resting meaning هيدي الكاينتيك energy بتكبه. Okay. So the mechanical energy here solely depends on the gravitational potential energy. So it solely depends on mgh. right? طيب, when is it gonna be 0? So when is mgh gonna be 0? Let's examine this. This is logic. Okay, when is mgh equal to 0? Can m equal 0? Never, right? It's 500. Can g equal 0? Never. We know it's not. So h has to be equal to 0. So where do you have to be standing in this case? Where do you have to be standing? You have to be at your reference point, right? When h equals 0, if the ground is your reference point, that means you're on the ground. Here, what's my reference point? If someone said 0 centimeters, of course you're very wrong. Why? Because we're saying relative to the second shelf, right? Relative to the second shelf. So if my car is on the second shelf, it should be 0, because my reference point is the second shelf, and in this case height would be equal to 0. But how high above the ground would this be? It's 2 shelves, and I think everybody here can figure out that each shelf should be 30 centimeters. If you're 2 shelves up, that means you're 60 centimeters high. That's it. Okay, so since we're at rest, kinetic energy isn't included. The only thing mechanical energy depends on is gravitational energy, potential energy, and gravitational potential energy relative to the second shelf would be 0 if it's on the second shelf, and each shelf is 30, so it should be 60 centimeters. Okay, if the toy car was not stationary but was instead moving along its shelf, what would my answer to A be? Okay, obviously it's gonna be small. Someone is gonna be like, okay, well, that's not obvious for me, man. Okay, mechanical energy. Remember, it's U gravitational plus kinetic. In the start, we cancelled kinetic because it was stationary, it was resting. But he said it's not stationary now. That means now there are 2 factors that play a part into now having, we're saying 0, right? Into getting 0, there are 2 factors. So we have mgh plus half mv squared. So now, since that I'm gonna be adding half mv squared, don't you think the value of this should be less? Like, مثلا, to get 0, you can use negative 10 plus 10, right? But if you remove this 10, this could be negative 20, negative 30, so on. I used a very, very bad example, but I hope you understand. You know, we were solely getting the 0 from mgh. Now the half mv squared came to help. So think about it like that, the half mv squared came to help. So it's decreasing the load on mgh, and therefore to get 0, you don't really have to have much mgh, so it's going to be smaller. So I won't really need that. Whoa, I'm stuttering. I won't need. I don't know how to speak English. I won't need a high height. You could say that. Question 9. A cannonball of mass 12 kilograms is shot vertically upward. Is vertically upward at 50 meters per second to reach a height of 80 meters. Shot vertically upward. It doesn't mean projectile. No, it just means it went up. Okay. Use g equals 10 meters per second squared. Choose the 0 level of the gravitational potential energy on the ground. Easy. The initial kinetic energy of the cannonball. Kinetic energy initial. Okay, K initial. It's equal to half mv initial squared. Type. Half mass 12. Type. V initial squared. This is V, 50 square. ما بدها الأد at all. Okay. Half times 12 times 50, so you could just say 60 times 50 squared. 6 times 50 squared, because half of 12 is 6. 1500, and they said in kilojoules, so 15,000 in it's joules, obviously. In kilojoules, you just divide by 1,000 and you get 15. The mechanical energy of the cannonball at the topmost point of its trajectory to one decimal place is what? Remember, where they said neglect air resistance somewhere. No. Okay, so people here, they're gonna be like, okay, mechanical energy 1 is equal to mechanical energy 2. So if you just have mechanical energy 1, then mechanical energy 2 is gonna be the same. They never said neglect air resistance. Since they never said neglect air resistance, although in some questions they like, it's kind of obvious, they didn't say neglect air resistance, but you can solve. If you look at part C, they said energy was lost as heat. So you can't say mechanical energy 1 is equal to mechanical energy 2. Never. So you're going to use the traditional way and actually find what is mechanical energy. Mechanical energy is equal to U gravitational plus kinetic energy. And since we're not working with the spring, so there's no U elastic. They're saying, when is the mechanical energy? At the topmost point of its trajectory. At the topmost point. فأنت بتطلع لفوق over here. At the top point, am I still moving? No, I stop for a second and I go back down over here, right? Exactly. So at the topmost point, V is equal to 0, right? So that means kinetic energy, there will be 0. So mechanical energy at that point will be equal to U gravitational, which is equal to mgh. So it's equal to the mass, which is 12, times g, which is 10, times the height, which is 80 meter. And when you get this, you get 9,600 joules. But they want it in kilojoules, so divide by 1,000, you get 9.6. The amount of energy dissipated as heat on the way up to one decimal place is how much? For this, you can use the formula energy lost or work lost is equal to delta U plus delta K. You can use this. But for this sake, it's easier, I think, for you guys. It makes more sense to just use how much the final mechanical energy was and compare it to the initial mechanical energy, right? Compare how much was lost. So at the start, we had 15 kilojoules, right? There was 0 gravitational energy because it was at the 0 level, at the ground, right? Then in the second, the mechanical energy was 9.6. So ME1 was 15, and ME2 was 9.6. So actually, it lost 5.4 kilojoules. Very, very easy. Okay, it's way easier to do this since you have both given to you. But we use the formula delta U plus delta K. When you don't have the mechanical energy, it's a bit harder to find them. Okay, and especially when you're working with friction. When you're working with friction, it's a pain in the ass. You use delta U plus delta K. And you'll see now they're not going to give you these hard questions for AMSs, inshallah, but for your periodics on the soon. Compare the work done by the drag on the cannonball on the way up to that on the way down. The work done on the drag by on the cannonball on the way up is obviously greater than the work done by the drag on the cannonball on the way down. And they asked to explain, obviously because the drag going up is greater than the way down. يعني انت فكر فيها, okay? You're going up, right? You're trying to jump, or you throw an object up. You have the weight resisting the force, and you also have the drag pushing you down, the air resistance. However, if you're falling down, you already have the weight pulling you down, and you already have the drag pushing you down. So obviously it's gonna take more force on the way up. The drag air resistance is gonna be greater on the way up. Think about it into what's easier, what goes faster, the point, and let's say you have a ball, you throw it up. What goes faster, when you throw it up or when you throw it down? Obviously it goes faster when you throw it down because there's less air resistance when you fall down. Question 10. Oh my god. A spring of constant 4,000 Newton meter is compressed from both sides from two blocks of masses MA and MB. Which of the when the blocks are pressed against each other, the deformation of the spring is 5 centimeters. The blocks are released from rest and move away from each other along a smooth frictionless floor. The initial amount of energy of the block spring system is how much? We're gonna start. أول شيء you have, I'm gonna try and draw it for you. You have the spring connected to block B over here, connected to block A over here. They push both, and now it compresses, and SATA block B is like this, and block A is like this, so it's compressed. The elongation is how much? 5 centimeters, and they gave us the constant. We don't know anything about their velocity. There's no velocity, there's no movement. We don't know anything about change in height, so there's no gravitational potential energy. So the only energy here would be elastic energy, because we have a spring, obviously. And how do you find U elastic? It's equal to half kx squared. So half times 4,000 times 0.05 squared. Why 0.05? Because it's 5 centimeters, so 0.05 meter. So put it on your calculator. 0.5 times 4,000 times 0.05 square, you get 5 joules. The net kinetic energy of the block system when they move independently, it's obviously also 5 joules. Why? You're going to be like, why? They're saying of the system. Okay, not each block, how much, which one has 5 joules, which one has 2 joules, which one has 1. No, we don't care. Of the whole system, when you release them, how much do they have? It's 5 joules. Why? Because they said a smooth frictionless floor. Nothing is gonna dissipate energy or absorb energy. There's no reason for any energy to be lost, right? It's a smooth frictionless floor, فأكيد it's gonna be 5 joules. The ratio of the average acceleration of the blocks when the spring is expanding, acceleration of A over acceleration of B is how much? Over here, when it's expanding, the spring shoots it with a force F, and over here shoots it with a force F. It's the same force, right? And we know masses, accelerations, force, F is equal to ma. F is equal to ma. Let's call it maa and mab. Okay? Acceleration of A is equal to F over m. Acceleration of B is equal to F over m also, but mass of A, huh? And then mass of B. Type, okay, well, what's, okay, what? This force is the same. It's the same. What's different here is mass of A and mass of B. So acceleration of A is going to be equal to F over 2 kilograms. And acceleration of B is equal to F over 4 kilograms. So the ratio of acceleration of A over acceleration of B would be F over 2 divided by F over 4. And when you divide, you flip. So F over 2 times 4 over F. Cancel F with F, 4 with 2. You get that the ratio is 2. Very simple. I did the long math way. You can just say when it's a spring, anytime you see this case, when it's a spring, you just divide. If it's acceleration A over acceleration of B, it's equal to mass of B over mass A. You do the opposite. Okay? Anytime you have two springs shooting like this, since it's the same force, you can always just use the masses. The kinetic energy of block A, just as it leaves the spring to one decimal place, is how much? For part D, it's a bit trickier, but it took me a while to solve, but I finally figured it out. Basically, you can actually find the accelerations A and B, okay? Because what happens is when they leave, they accelerate, okay? You can find the acceleration. How do you find the acceleration? It's F over 2 and F over 4. We know that the spring has a constant of 4,000, but we know that the spring has deformation 5. And you know that actually F is equal to kx, right? So you can do 4,000 times 0.05, and you get 200. So that means acceleration of A is going to be 200 over 2, which is 100. Acceleration of B is 200 over 4, which is 50. Perfect. Hella, you have the acceleration is 100. They're asking for the kinetic energy just as it leaves the spring. So the spring was compressed 5 centimeters. It's accelerating at 100. And how long does it accelerate for before it leaves the spring? It accelerates for 5 centimeters. So that means you have this 5 centimeter interval at which it's accelerating at 100 meters per second square. Can you find the velocity knowing that you have acceleration 100 for 5 centimeters? Of course you can. V squared minus u squared is equal to 2ax. So v squared is 100, we don't know it. U is 0 because we're starting from here from rest. Okay, equals 2 times acceleration 100 times 0.05. So v is equal to root all of this, and you're going to get root 10 if you do it on your calculator. I did it over here. Okay, so now you know that the velocity of A is root 10. What's the kinetic energy? It's half times the mass, 2 times the velocity squared, so root. Okay, for part D, you need to use part C. The ratio of the average accelerations A over B is 2. This also means that velocity A over velocity B is also 2. For this case, why? Because it's on the same spring, block A and block B. Same spring. The average accelerations, the ratio between them is 2, so the ratio between the velocities should also be 2. Because they're both on the same spring and it's the same deformation, 5 centimeters, whatever. So velocity A over velocity B should also be 2. The proof for it in ChatGPT, I had to use ChatGPT because I was low-key lost, but it's because they used momentum, but you're not required to know momentum. Anyway, so VA over VB is 2, also because the accelerations is 2. Type. So that means also that VA is equal to 2VB. Now what are we trying to find? Kinetic energy of A and kinetic energy of B. We know that kinetic energy of A plus kinetic energy of B is equal to 5, right? We said it here. The kinetic energy of A is half mv VA squared. Kinetic energy B of half mvb squared. But isn't VB just VA? Isn't it, sorry, isn't VA equal to 2VB? Yes, it is, right? So you can substitute this VA with 2VB. You're gonna get now half m VB, sorry, 2VB square outside plus half m VB squared. 2 squared is 4. So half 4 VB squared. You know how to do this, right? 2 squared and then VB squared. Okay, plus half m VB squared and also half m over here. Add these together, you're going to get half m times 5 VB squared, because 4 VB plus 5 plus 1 VB. Okay, this is all equal to 5, right? Multiply by 2 on both sides, you're going to get 5 VB. Okay, for part D, you can use the same ratio for part C. Acceleration of A over acceleration of B equals 2 means also that the velocity of A over velocity of B is equal to 2. Why? Because it's the same spring, same distance, same interval. Okay, so it's the same thing for the ratio of the velocities. Okay. Now, since you know velocity of A over velocity B is equal to 2, you know that, in other words, it's equal to 2 velocity B. You can use this over here, because now we know kinetic energy A plus kinetic energy of B is equal to 5. If you didn't do the step, you would have done it after you write this, because we know that the total kinetic energy is 5, right? So half MA VA squared plus half MB VB squared is equal to 5. طيب. Can't you substitute VA with 2VB? Of course you can. So half MA 2VB squared is outside plus half MB VB squared equals 5. Square this. Half MA 4VB squared plus half MB VB squared is equal to 5. Okay, let's start substituting. Half MA is half times 2, which is cancelled, so 4VB squared plus half MB, so half times 4 VB squared is equal to 5, so 2VB squared is equal to 5. So 6VB squared is equal to 5, so VB squared is equal to 5 over 6, so VB is equal to or you not keep it as squared, because when you substitute this now into the kinetic energy, you're keeping it as squared also. So now can I find what the kinetic energy of B is, knowing that I have the velocity of B? Of course I can. So kinetic energy of B now will be equal to half MB VB squared, so half times 4 times VB squared, so 5 over 6. So 8 times 5 over, 2 times 5 over 6, so 10 over 6, which is 10 divided by 6 should be 1.7. Yeah, 1.7 to 1 decimal place. Okay, so 1.7. طب how about kinetic energy of A? You can simply just do 5 minus 1.7, or you can substitute VA is equal to 2VB, so VA is going to be equal to it's going to be equal to 2 times VB, right? VA is equal to 2VB. Then we have VA squared, so if you square both sides, you're gonna VA squared. Shit. We have VB squared, not VB. You want to use VB, you have to square with this, but I don't want to do it. Instead I'll square both sides. Okay, so I'll get VA squared equals 4VB squared. So VA squared is equal to 4 times 5 over 6. So you cancel 20 over 6, you get 10 over 3. Okay. And so you get 10 over 3 for VA squared. So now you can go back. So kinetic energy of A is actually half MA VA squared. So you substitute this with 10 over 3, this with 2, this with half, cancel. So you're going to be left with 10 over 3, which is 3.3. It's quite long, I know, but these questions, you probably won't see them in your exam. They're just filler questions. Question 11. The graph below shows the variation of force F on the spring necessary to compress it by x centimeters. The potential energy stored in the spring when it's compressed by 4 centimeters is what? So over here at 4 centimeters, we can simply use half kx squared. But although you may not know k, you need to find k. Why? How do you do it? F is equal to kx. At 4 centimeters, you can find k. K is going to be equal to F over x. The force at 4 is 18, because the graduation is 2, over the elongation, which is 0.04. Let's find it. 18 over 0.04. 450. So over here we can use half times 450 times x squared, so 0.04 squared. So 0.5 times 450 times 0.04 squared. You get 0.36 joules, right? Type. The spring is compressed by 4 centimeters and the 500 gram block is attached to it. The greatest speed that this block can develop to 1 decimal place is something meter per second. So we found, remember, the greatest speed, you always work with mechanical energy. So mechanical energy 1 is going to be equal to mechanical energy 2. At the start, there's nothing. There's no height, there's no GPE, there's no kinetic energy. So remember, mechanical energy is kinetic energy plus gravitational energy plus elastic energy. Kinetic energy will be 0 because the block is at 0, right? It's not moving. The gravitation is 0 because there's no height. We're not given any hung or whatever. It's not hanging anywhere. So we only have U elastic, and we found U elastic at 4 centimeters to be 0.36. Okay, equals ME2, which is going to be, again, same thing, U elastic, UG, and ME. U elastic will be 0 because it's not attached to a spring anymore. UG will also be 0 because we're not changing height, plus K final. So obviously, we're going to be left with the U elastic is equal to K final. So 0.36 is equal to half mv squared. Let's do it. 0.36 is equal to half times mass of it is 0.5 kilo times v squared. And you can find the velocity easily. So 0.5 times half, which is also 0.5. You get 0.25. And then now this 0.25 divided by on both sides. So you're going to get 0.36. divided by 0.25 and square rooted, you get 1.2 meter per second. Question 12. A block of mass 200 grams is sliding uniformly down a plane inclined at 30 degrees with the horizontal. The block moves through 30 centimeters across the plane. Okay, so drag and drop the correct answers and to state the work done by each of the following. Normal reaction, weight, friction. Okay, normal reaction is always 0. We can skip it. Weight and friction. Okay, this is extremely easy. To understand this better, I'm going to draw the FBD for you. You have, this is the 30-degree plane. This is the y-axis. This is the x-axis. Okay, you have the weight, which has its components wy, wx, and you obviously have the friction. Okay, so it's sliding uniformly. Okay, you also have the normal, no? It's sliding uniformly, so sigma f is equal to 0, right? So our sheet, that means sigma fy is equal to 0. We know, obviously, that we don't care about the normal, but the normal will obviously give me 0, right? And sigma fx is equal to 0, meaning that friction is equal to wx, right? As in forces, no? And wx is actually, in this case, the angle here is 30, right? Remember, for inclined plane, the angle between the vertical and the force is equal to the angle of the plane. So friction is going to be equal to mg sine 30. So friction is going to be equal to the mass 0.2 times g, which is 10, times sine 30. So the force of friction is going to be 1. It's actually going to be 1. Is it 1? 0.2 times 10 times sine 30. Yeah, it should be 1. So friction is going to be 1 Newton. So are you asking for work or friction? Work. Work is equal to force times distance times cosine, the angle between the force. Right? Okay, the movement is down. Friction is the other way around. So the angle is 180 degrees. Teachers solve like this. But Anna, for me, when I'm solving for friction, without putting the angle, I just put it's equal to negative force times distance. Why? Because friction is always in the direct opposite direction. So work is going to, the work of friction is always just equal to the negative of the work done. Okay, so negative, the force of friction, 1 times the distance, which is 0.3 meters. So it's going to be negative 0.3. So the friction is negative 0.3. The weight, however, will be mg sine 30. The force of it is mg sine 30, right? Which we found to be 1 Newton. But the distance of the work, since we're moving in the distance of the work, the weight is pushing to the left, we're moving down to the left. So that means it's just going to be force times distance. So the work done by the weight now is equal to force times distance. The force of the work is 1 Newton. The distance is 0.3. Why not negative? Because it's moving in the direction of the weight. But friction is always negative because it's the opposite direction. As the block slides down the plane, what happens to the power developed by friction on the block? We're moving uniformly. The work done is not being changed. Okay, so power is equal to work over time. Since we're moving uniformly, the power developed by friction remains constant. Question 13. A small block is projected from the edge of a smooth horizontal table at 2 meters per second. The mass of the block is 200 grams and the table has the height of 0.7 meters. So you can kind of say like this. This is your table. Top of the table. Okay, and you have your block over here. Okay, and the height of the table is 0.7 meters. Perfect. Use G equals 10 and take the zero level of gravitational potential energy as the surface. So the surface of the table is the zero level. The initial mechanical energy of the block is what? So let's see. Mechanical energy 1 is equal to UG plus K1. Obviously no elastic because there's no spring. K1 is 0 because it was at rest. Balakis, no. It wasn't at rest. It was projected at 2 meters per second. So it's not 0. Okay, so the UG is actually going to be 0. Why? People will say, oh, isn't the height 0.7? No, the height at the start is actually 0 because they said take the reference as the table, right? So UG is 0. So what do we have only at the start for mechanical energy 1? It's just K1, right? So K1 will be half times the mass. The mass of the block is 200 grams. And the velocity is 2, so 2 squared. Why am I using the velocity now? People say, no, always at the start you don't use the velocity, it's always 0. No, man, no. Mistake. It was projected at 2 meters a second, so it started at 2 meters per second. Projected, yani they hit it, okay? So half times 0.2 times 2 squared, and you should get 0.4, but let's do it anyways. 0.4 times 0, okay, 4. 0.5 times 0.2, sorry. 0.4. Perfect. The speed of the rock when which it hits the ground is what? Now we do ME1 equals ME2, right? So ME1 equals ME2. ME1 we found to be 0.4. ME2 is equal again K2 plus UG2. Type K2, it's not 0 obviously because it's falling. UG2 will also not be 0. Why? Because it actually has height. Even though it's on the ground, it's below the reference point. So its height is negative 0.7 meters. Okay, so ME2 is going to be equal to K2, which is half times 0.2 times velocity squared, the new velocity, whatever, plus mgh. Type. Let's continue. ME2 is going to be equal to half times 0.2 times velocity 2 squared plus the mass 0.2 times g which is 10 times the height, which is negative 0.7. And you can solve this easily. We need to equate this to how much? ME1, right? Remember ME1 is equal to ME2. So this equal to 0.4. So let's do it on our calculator. Half times 0.2, okay. So let's do this on the right first. 0.2 times 10 is 2. Should be negative 1.4 over here. So minus 1.4. And here you have half times 0.2 is 0.1. V2 squared is equal to ME1 0.4. Solve this, you get 1.8, you get 18. You should get square root of 18. If you solve it on your calculator, you get 4.2 to 1 decimal place. Easy. Select the correct diagram that shows the variation of the power developed by gravity on the block. Power is equal to the change in work divided by time, or force times velocity. Since velocity is increasing, The force is constant. It's gravity. It's why are they saying by gravity? It's constant. It's increasing at a constant rate because the force is constant. But the velocity is changing. Well, why is the force constant, by the way? Because it's the weight. The gravity pulls it down with the force called the weight, and the weight is always constant as long as you're in the same planet. The velocity is changing. It's increasing as you're falling down, right? So for that reason, the power in that case will also increase. Simple as. Question 14. A car of mass 800 with its engine shut off descends at a constant speed of 10 meters per second down a hill inclined at 5 degrees with respect to the horizontal. The amount of energy dissipated as heat every second to one decimal place is how much? So for the energy dissipated as heat every second, we're talking about friction, right? In other words, we're saying work done by friction, right? The work done by friction is equal to the force of friction times the distance. And for that reason, I drew the FPD to see how much the force of friction is. Over here, you have y-axis, x-axis, and obviously the angle, like they said, is 5 degrees. So you have your weight like this. It's 5 degrees. And you have, this is mg sine alpha, because it's the x component of the weight, right? And over here, backwards, you have your friction. Type, okay. How do you find the force of friction? Obviously, since we're moving at a constant speed, sigma fx is equal to 0. For that means f is equal to mg sine 5. So 800 times 10 times sine 5. Okay, you're gonna get 697. Okay, point something. But we're saying work, so it's force times distance. So 697 times the distance. Work as heat every second. We know that we're moving 10 meters per second. So every second is 10. So distance is going to be 10. So it's going to be 6,970. So it's going to be 2 kilojoules to one decimal place. It should be 7.0 kilojoule. Okay, you get it over here. Okay. They said the amount of energy dissipated. That's why they didn't say work. Work, you'd put it as a negative answer because remember, work done by friction is negative Ft. But they said amount of energy. They don't care. The driver applies the brakes to gradually decrease the speed of the car to 5 meters per second. How will this affect the magnitude of each? The kinetic energy of the car obviously will decrease because you slowed down. The rate at which the potential energy of the car is converted into other forms of energy will it should also decrease because the kinetic energy decreased and you lost a lot of energy as heat. Yeah. Since you slowed down, your potential energy graph, instead of decreasing like this, now it actually is decreasing like this. See how it's like slower now? Okay, so that means it won't be converted. It's going to be converted, but it's going to be slower. It's just going to be way slower. Okay, question 15. A water can pump 5 kilograms of water through a height of 2 meters per every second. The power output of the watt is what? Okay. Obviously, for this you're gonna use P is equal to force times velocity. So the velocity is obviously 2 meters every second. So 2 times the force. Since it's pumping it up, the force is actually gonna be the weight, right? So the weight is equal to mg. So the mass 5 times g, which he said is 10. 50 times 2 is 100 watts. Which of the following is a likely power input of the pump? What? Yeah, power greater than P. Obviously, yeah. It's an input of the pump. Obviously, you're going to use power greater than 100 watts. If they use 100 watts, it might run out. Which of the following can be reasons for that? Yeah, dissipative forces exist within the pump. They're not going to use something exactly 100 because there might be friction, there might be whatever. So you're going to need more than 100 because energy will be lost. I'm going to stop talking. That's enough talking for one day. We'll lead mechanics done. Thank you so much for watching. Good luck.